Yeah, I mean, if you can maybe like fold them like this person did.
Okay.
Yeah. Cool. Awesome. Yeah, perfect. On the top there. Is everyone's check-in? Brad. Yes, I don't know. I'll remember next time. Okay, how's everyone doing?
Good.
How's everyone doing? Some goods, some mediums. All right, medium to bad. Okay. Check in okay. Reasonable amount of work. Feeling good about yourself? Um, so this is obviously not a real picture, but perhaps I'm going to age myself here. So when this was coming out, you know, maybe many people maybe grew up thinking that Pluto was a planet. I don't know if you didn't. So if you didn't, you may want to understand why this has been controversial. And it's not like they all got together and ganged up, although these sizes are kind of accurate, not exactly accurate. But I think this does feed in really well to understanding how terrestrial planets, that is planets with rocky surfaces, how we can extend that model of understanding their surfaces to the outer planets and also to icy bodies. Okay, and we're going to start with some moons, and then we're going to talk about Pluto. And Pluto is actually one of a different class of objects. It's not like anything else. Okay. Yeah.
Like the constant updating, like so like you said, like there's what is considered a planet or not. You know, growing up, they did tell like it was a planet and then.
Yeah, so that only comes from one update. We don't change definitions very often. We'll talk about how that was chosen as well. Controversy in science. Okay, so we were talking about icy planets. We talked about this one, Europa. That's the second moon at Jupiter. And we think that it has a subsurface ocean. Probably this one on the right of these two ideas. JUICE launched last year. That's a funny name, but I don't know. Astronomers not very good at naming things. Arrives at Jupiter in 2031. So stay tuned. Just 7 more years. Something like that. Okay. And what it'll do is it'll fly very close in order to see if it can understand the properties of the subsurface ocean. The ice crust, we think, is something like 15 kilometers thick. And the farthest we've ever drilled here on Earth is about 12 kilometers. And it took us almost 25, 30 years to do so. So we're not going to land there and drill under the surface and like go look for sharks and whales. Okay. Just like revise our expectations. One of the many reasons I say that aliens have never visited us has to do with this. We are not the most important planet by a long shot. So if you're going to go somewhere, like let's say you get in your car, well, I guess maybe kids don't do this anymore. You ever just like drive around for no reason? Yeah, some people do. Sometimes you drive around for no reason, but now with like the cost of gas, right? You're really going from point A to point B. So maybe you need to go like pick something up from 7-Eleven, right? So you drive that distance to get the thing. So imagine the nearest 7-Eleven is like 4 light years away, right? You're not going to not pick something up. So if you're going to grab something, you grab the tastiest thing, which is the water. Because everything that we understand that is life uses water. And who has the most water? Europa. So if they're going to come to visit, they're going to come visit Europa, and they're going to drink all the water there first. Yeah.
So what's the scale?
Yeah.
Is the water in Europa bigger, or is it just because there's more water per Europa? Like, because Europa is a smaller like moon, and there's like more water compared to the they look the same size.
Yeah, the total content is more.
Okay.
I mean, they're very slightly different. It's almost comparable. The water per Europa, you're right, it's much larger. Because Earth is obviously. Right? Okay. Europa has only ice tectonics, while Io has many volcanoes. We were talking about why this might be. Tidal heating on Europa is weaker than on Io, mainly because Europa is smaller than Io, because Europa is farther from Jupiter, because Europa is not in an orbital resonance, because tidal heating is not important if liquid water is present, or none of the above. Tidal heating is greater on Europa. Wait, hold on. Let me start the poll. Okay. That working? Yeah. All right, there we go. You remember how tidal heating works? Okay. Hey, click in if you want to click in here. Okay. Looks like half of everyone likes one answer. And then the other half likes all the other answers equally. Anyone want to defend their decision? Yeah.
I think it's B because on last class, you showed us that, I, what was it, Io is closer to Jupiter, and, you showed us that it's connected to like the magnetic fields, and I feel like it has something to do as to why, Io has more heat and has more volcanoes and well, it's a lot farther away and didn't ask, but I might be wrong, but that's my logic.
Okay. So I heard a lot of things in there, and I'm gonna pick out the parts that I agree with.
Sorry.
No, it's okay. No, that's the right way to think about these problems, right? You want to see if you can connect all the pieces. So you said that Io was closer. That's 100% correct. You said Io had volcanoes. It does. Europa doesn't have volcanoes. And it is farther, right? And so the question is the tidal heating weaker on Io? Maybe that's the first thing to ask. Because the last one here says it's great. Is that a lie? Yes, that's a lie. The tidal heating on Europa is not greater than that on Io. Io has had volcanoes on it pretty much continuously for its entire existence. Right? Okay, on Europa, you just have a surface that's sort of icy and melty. You don't have volcanoes. One of those takes a lot more energy than the other. Okay? So we can get rid of that one. And now the question is, the tidal heating on Europa is weaker. So why? So Europa is not smaller than Io. Europa is in an orbital resonance. And tidal heating doesn't care if liquid water is present. So the reason why tidal heating is more important on Io than Europa is because Io is closer to Jupiter and Europa is farther from Jupiter. The way you can think about this is gravity acts more strongly on things that are close to things. If you're very far away, the gravitational attraction is not very important. For example, we're much more interested in the gravitational attraction of the Earth than we are of Jupiter. The Earth is right below us, despite Jupiter being very large, but very far away, right? Okay. We're not going to be able to do all the moons. You could have a whole class on moons. Pretty sick what's out there. But we're just going to talk about a few of them, and then we're going to talk about that little guy down at the bottom. We talked basically about these two already, Io and Europa. I want to tell you a little bit about this one, called Enceladus. This one, Titan. We'll talk a tiny bit about this one, Triton. But there's a whole class of objects that you'll just never see. This is Enceladus. This is one of the moons of Saturn. The size of Colorado. If you've ever driven across Colorado, it takes about like 4 or 5 hours. You could drive across this moon. These are the tiger stripes I told you about earlier. What do you notice about this terrain compared to this terrain? Say that again? Yeah, less craters. I mean, over here, I can barely find any, right? If I look in this region, where these lines are, I really don't see any of them. And here I can see plenty, right? So this has to be like brand new material, less than 500 million years old, right? That's weird. Is it weird? Go back 1 second. This is how big it is. There's Enceladus, and there's Europa. Enceladus is small, right? It's not everywhere that the surface is new. Certainly at the top here is an older surface, but it is an icy body. And this icy moon of Saturn has a very unique property. It has plumes. And we've flown through these plumes, not me and you, but humankind. No, robots have been sent by humankind to fly through these plumes. This material here is coming out of these tiger stripes. So these blue cracks are actually fissures to a subsurface ocean that's being pressed up out of the planet like a geyser. But it happens all along these stripes. And then when it falls back down, it makes the surface free from any craters, right? It's a resurfacing event. So imagine just like hundreds of thousands of Old Faithfuls all up and down this region, right? It's not a global phenomenon. On Europa, we saw that this resurfacing was global. Looks like there's probably ice underneath the surface just in this region and maybe not over here. So this is kind of what the visualization we think about. Probably a rocky interior, ice on the top, but somehow there's a global, or not a global, a southern hemispheric oceany magma type thing. Kind of weird words to use when you're thinking about what is the state of ice below the crust. Because this is an icy crust, and this is like some form of liquidy solution. Okay. This one's really cool because you can fly through it, and that's a direct access to this. And so we have flown through it with spacecraft, and you have spacecraft or instrumentation that allows you to like find out what's inside. So we know exactly what types of minerals are in the water. The coolest thing about this, anyone here like a biologist or no biology? Okay. So organics that make up our DNA, they're long and heavy. And so we can weigh different material. We can split up like the material and basically weigh it. So like hydrogen is 1, and helium is 2, stuff like that. So really long molecules have a heavier weight. When we sent something that can do that to this location, it had all of these different bins that it could weigh in up to a large number. And it filled up all the way up to that number. It didn't run out of space. So there's probably even longer chain molecules that exist in this solution that we have to send a new instrument to find out how complex those molecules might be, right? So that means that instead of just finding things like CO2 or CH4, there might be long string polymers that would be the basic building blocks for life underneath the surface. So this one's great because you don't have to dig into the surface at all. But again, you won't be able to like take photos of whales. Right? Make sense? Okay. The next one is come on now. This one is also a moon of Saturn. This is called Titan. And this is a real picture. So Titan looks weird. Titan looks like Venus, right? They are very, very different. If this works, this is the descent probe. So we sent a spacecraft there called Cassini, and we landed a probe called Huygens. And it's going to go through the atmosphere, and it's going to land on the surface. And it's going to take photos of the surface. And on the way down, it's going to tell us what the atmosphere is made of. So hopefully this video works. Piercing? Okay, the beginning of next class. I'll make it work. It's a really cool probe. This is what it looks like. So at the very top of the atmosphere, it's this weird like orangey, hazy stuff. And then as you fall through the atmosphere, it looks a lot like there are mountains all over the place. And you fall even farther. This is from the surface of Titan, and this is from a beach here on Earth. I have no idea. Yeah. Do you see any erosional features here? Yeah. Is that strange? The moon, right? Now it is Titan, Titan being large, right? It's the largest moon. So, okay, that's maybe it's got some heat left over, but that's not the primary reason why you can have hydrology here. these features that you see on the top of these mountains that are carving this out, this is from what is essentially a hydrological cycle, except not using water. So the hydrological cycle on Earth is ocean evaporate, become cloud, cloud move on to land, snow or rain, create river, back into ocean, right? They do that here, but with methane. So you'll have methane lakes that evaporate and become methane clouds, and they go over and they rain down. The methane carves rivers, and that goes out to methane lakes again. So here on the right-hand side or the left-hand side of this right-hand image, you see these like rocks that are rounded, and they're sitting in essentially what is like a beach. And that's kind of exactly what you see here, which is like if you have waves that are pressing rocks and rolling them, they tend to lose their smoothness, and they form this kind of a unusual rounded feature. This is another image of Titan. What you're seeing here is a composite of many images stacked on top of each other. They can't take one picture all at once here with the same resolution. What do we think that is? What's that? A lake or an ocean? And what about it makes you think it's a lake or an ocean? Yeah, glare is the word I was looking for there. This is the gleam of the sun reflected off of a lake on Titan. So that's another way we can tell there's standing bodies of water as opposed to just ice.
The reflection.
Yeah, exactly right. Yeah. So that's what you see there. It's scattered around in all these locations, but Titan is a really cool combination of planet where it's small enough that the gravity is not so big, but the atmosphere is dense that if you strap on, you make like wings like you would make for your kids' Halloween costume, and you start flapping them, you will be able to fly on Titan. Now you won't be able to breathe, but that's a different question. Okay. All right. Let me show you one more. This one we're going to talk about in a little bit more when we start thinking about what Pluto should look like. So that's us, hopefully. That's the moon to scale. This one's Triton. I know, confusing, Triton, work with me here. This is the images that we have so far. Sometimes when we fly by these objects, we only get one view, right? Like for Titan, we're in orbit, we make many passes by it so we can get a full image. This one, we just got one. So let me show you what we see here. Come on now. All right. This is the largest moon in the Neptunian system. It orbits backwards. That's kind of a weird thing, but we're not going to focus too much on it here. Have a look at that surface. What do you see? Ice? Why do you think ice?
Like the roof part, like that's at the top.
Like here?
It's like ice, but it's like not like fully frozen in this, or it's like it could also just be straight up water or some sort of liquid.
Okay. Okay. Anything else?
White and blue.
White and blue. Yeah, the colors are whitish blue. Yeah. Forest. Okay. Yeah. Okay, that's funny. So I always call this a cantaloupe. Do you see cantaloupe? Yeah.
Yeah.
So the texture here looks like those ridges, like holes maybe. Yeah.
I'll see it looks like something is almost dragging across it, like those linear lines.
Yeah, these lines. What do we think of as lines on planetary bodies? What is that called?
It look that way.
No. No, that was just a joke. What? Tectonics is the word, right? So it shows tectonic features on its surface. I don't really see necessarily erosion. Do I see impact crater?
Yeah.
We see circles, yeah. So there could be an argument, right? So there's like this circle here, circle here. If it is ice, perhaps it's, smashes in there and then gets deformed, right? But no one talked about any of these like dark spots. Volcanoes or let's zoom in a little bit more. Is that better? It's more like that. But you have these huge tectonic features going across the entire planet. Sort of strange rippled textures. If you're thinking about Europa, that's right. These are probably ice flows in the same way that Europa has ice flows and these tectonal features. A few craters, I think that's unarguably a crater. That's probably a crater. Those are probably craters. That's a crater, but pretty few. What are these? Yeah.
Is it a type of volcanism and that's just like the gas that's coming out from it?
That is exactly what it is. This is a special type of volcanism called cryovolcanism, where when you have a geyser, but instead of it spitting out water, it just spits out frozen ice material. And we'll see that that is reshaping the surface here. Okay, tectonic features, I said that. Not very many impact craters. Similar to volcanoes, they are volcanoes. That's not a real image, but that's an artist's conception of what a cryovolcano looks like. So this is an idea of what it looks like on Triton. And then in the background, you would have Neptune. Uranus? I forget.
Like a vapor or something, because I'm thinking like cryotherapy, their cold temperature is like you say, not a vapor, but it's like, almost like, I don't know how to say it.
So the reason that we use the word cryo there just means cold, essentially, right? So cryovolcanism is different than normal volcanism because you don't have magma coming through the surface, right? In the example with Io, you really do have the interior mantle coming out like lava, flying out, very traditional volcano, right? Here, it's like a geyser. Now, whether this is because of a subsurface ocean, whether it's a mixture of water and magma, we're not quite sure yet. But this is really like a cold volcano in a very different sense. Okay. All right. So when we think about the terrestrial planet, like the Mars, when we think about the Earth, radioactivity in the center is driving the heat. So generally speaking, a smaller body is going to cool off first. So if you're smaller, you probably stopped creating new surface and you just started looking old a really long time ago, right? Collecting impact craters, never creating new surface, never eroding that surface, right? Whereas if you look at any of the icy moons, you can add this new source of heat, and that's called tidal heating. And we see examples of that over and over here. Titan has another advantage. It's very large, so it's retained some of its heat. But all of the other ones that I showed you have the influence of tidal heating in order to make them not super boring. Okay. What you really want is you want elliptical orbits. Be great if they were like close to their parent body, and that way they could get flexed, and that would melt their ice. Okay. Yeah. Any question about that? So we start with the terrestrial planets, understand that model. Now we understand how to think about icy bodies. Okay. And now we're going to apply it to a place that we've never seen before. Fair? Okay. The Kuiper Belt is a disk of rocky bodies between Mars and Jupiter, a disk of icy bodies outside the orbit of Neptune, a sphere of comets that surrounds the entire solar system, or the plane of what? No, the plane that the moons of the outer planets orbit in. Right, no one got tricked by my answer, I suppose. Again. All right, click in if you haven't. I can't tell if someone's pitying me, but basically no one. I guess if you don't even pronounce it right, then people don't really believe you, right? So it's not this one. What's this one? The asteroid belt. Okay. And has anyone watched Star Wars? Okay. Does anyone know like when they're flying through the asteroid belt? Is that accurate? No. You could fly straight through the asteroid belt, put your like bandana on, fall asleep, you'd be fine. You're not gonna hit anything. Asteroid belt big, these things small. Okay. So it's between these two, and we'll learn about both of them in this class. The Kuiper belt is a disk. Specifically a disk of small bodies, small icy bodies that exists outside the orbit of Neptune. The sphere of clouds is called the Oort cloud. And this goes all the way around our entire planet, our entire solar system. This one's funny. A guy named, he was a Dutch astronomer, and he saw like 3 comets that were coming from weird directions. And he like did some back of the envelope calculations. And he said, I think there's like 1 million objects out there. And then people went and like for 100 years, like we tried to find how many there are. It's about right. That's pretty good prediction skills. He just looked up and he's like, there should be other stuff out there. And so he gets it named after him. His name was, I believe, Jan Oort. Oort. Okay. So here's why we're talking about Pluto. We want to really think about how Pluto fits into this idea of the information you have about the solar system. Where does this surface fit into the surfaces that we've seen so far? What did we know before New Horizons arrived, which is a spacecraft that arrived in 2015? Hopefully everyone was alive for that. And what have we learned since? Okay. These are the planets, mostly in order. Okay, that seems inaccurate. All right. Don't understand why that's happening. All right. Sorry about that. Well, you just saw the whole slide. Let's go back. Yeah, right. Fastest way to do lecture. All right. So if you know this mnemonic device, how to remember them in order. My very energetic mother just sent us 9 pizzas. Well, since we got rid of Pluto as a standard planet, you can just drop the 9 pizzas and turn that into nachos, right? And that's obviously more realistic, right? Because your mom's never sent you 9 pizzas. She's definitely brought you nachos. Okay, so let's ask the question of what is the definition of a planet, and why is Pluto not one? Okay, so I'm going to let's imagine that you're all very qualified astrophysicists, and you're at a conference of other well-qualified astrophysicists, and you need to create a definition. Okay, so in order to be a planet, you have to be these things. So now, what are those things? Oh, hold on, it's not shot all at once. All right. Ramp. Okay, I like ramp. Okay.
You have to get a specific size.
Okay, maybe you have like a size limit. Orbit the sun. Okay, interesting. As opposed to another planet. So if you qualify as a planet, right? Okay. Yeah. To clear your orbit. What does that mean? Okay. Yeah, if there's other junk around. right? You can't have that nearby.
I was just thinking it should be part of the solar system, there should be something interesting about it. So like, there could be like.
Oh, interesting, right? Interesting is, that's a rough, as scientists, round, we can say round.
Yeah.
Right? Interesting, I could always argue that something's interesting. If I talk about it, it's interesting, right? Okay, so I like these definitions so far. I heard round. I heard it orbits the sun. And I heard that it has to do something like clearing its neighborhood. We'll see if those are true. So I'm see if this works. Come on now. All right. In 2006, this was the definition. Orbits the sun. Okay, and is big. Now, here's an interesting thing about is big. Does is big mean it's round? What?
Yes. Floating in space.
But what would happen to a large enough desk? Yeah, it would round out. Why was that?
Gravity of it, it just pulls it into the center and the differentiation.
Right. So think about all the processes that we've seen in the solar system so far, right? If you're really big, right, you need something that's going to sustain you, keep you up, right? Otherwise, you just crush down into a sphere. So if you really are large enough in mass, you're probably spherical. And that's part of the definition. Big, not raised up mass. You're massive enough, then you're probably spherical. Once you're spherical, you're good. Okay? And this was good for a long time. People were like, why would you need anything else? Round goes round the sun. Easy. Okay. And then they had to fix it. Okay. And you can go to these there's a website where they like put this meeting that all these astronomers went to. They didn't invite me because I was still a kid. And they decided on new words to add. So here's the definitions of a celestial body that becomes a planet. Has to be in orbit around the sun. Has to be big. Sufficient mass for its self-gravity to overcome the forces that would keep it up. We were talking about a desk. So if I can sit on this desk, right? Not crush it. Thank God. That for me. So if I had crushed it, then I would have overcome the rigid forces, right? These are rigid body forces. Okay, so if you're big enough, you'll crush everything, regardless of what it's made of, right? Okay. Such that it becomes nearly round. Now, nearly round, we have to throw in there because even the Earth is not perfectly round. Got a weird bulge in the center because it's rotating. Okay. And then it's this one, clearing its own neighborhood. Dwarf planet, just a smaller type of body that does not clear its own neighborhood. So it's still in orbit around the sun, still can be nearly round, and is not a satellite. Anything that we make is a satellite. Anything that goes around another object that is not the sun is a satellite. So for example, we talk about moons. Moons are satellites. How many moons does the Earth have? Raise your hand for one. Raise your hand for two. Correct, we have two until like mid-November.
Oh,
This is a very good question, and my student asked me this morning, and I think we could. So we're gonna try and do that at the next open house, just to see if we can like spot it with a telescope. It'll be fun. It's not like gonna look cool, it's a rock, but it's a rock in space. It's our moon for like a month and a half. I think they're called moonlets, but whatever. Okay. Right now, it would not be a dwarf planet because it's probably very not round. And of course, it's orbiting. It's not orbiting the sun. Okay, it's orbiting us. Okay, all other bodies except satellites should be called solar system bodies. All right, We understand this definition? Okay, let's see that.
Why are we-
That's a good question. We'll see. All right, vote in if you haven't. 3, 2, 1. Okay. Basically, two camps here. Some folks think it's too small. Some think there are too many other objects in its orbit. You want to defend their answer?
Regarding the classification of Pluto's planet, they would have to like there are other small planets that would be the solar system. So we look at a series that would be.
Oh, right. Interesting. The series is where
Yeah.
asteroid belt. And is there other stuff in the asteroid belt? Yeah, there's lots of stuff in the asteroid belt, right? So Ceres is round. Ceres orbits the sun. So Ceres then would have to be a planet, right? By that old 2006 definition. But because there's other stuff nearby that is similarly not orbiting Ceres, but orbiting the sun, then by definition, right, it's a dwarf planet. So planets have to have cleared out everything nearby. And because Ceres lives in a space with a lot of other rocks, where not its moons, there are too many other objects in its orbit, just like Pluto. But Pluto, Ceres, both dwarf planets. And we'll see that better here. Okay. Pluto was discovered in 1930 in Arizona. You can go here. This is in Flagstaff, Arizona, the Lowell Observatory. And if you've ever come up to the observatory here, they'll explain like how this camera here is like the result of astronomers getting bored of staring at photographic plates. So what they used to do is like take the telescope and put chemicals out on the giant mats, and then they would cover them, develop an image, and then go back and look and do that again, like night after night, and try to look for things that are moving in the images. Now imagine, like one of these spot the difference, but you're looking for tiny dots of light. So that's why you develop CCDs, because then you can just subtract the two images and stuff shows up really easily. So this process in 1930, pretty impressive. It's essentially doing it by notes and by eye, right? Looking for any object moving against the background of stars. Because how do we think of planets? Planets are the wandering star, that Greek word wandering star. And so he was looking for a tiny movement in the sky. Can you see it in these two images? What good the sky?
Is it a small one?
Yeah. It's the line. Yeah, and where does it go? Back there. Okay, I'll do it too. All right, so that's Pluto, and you can see it just because it moves against the background. Right? Is it giving off its own light? No, that's reflected light from the sun. We obviously can't tell the difference when you're just staring at it like this, it just looks light. But sun, very bright. Okay. That's me when not me, that's the telescope that that's a telescope. But I went there last year, and you can go see it. And they have the exact room, the same telescope that he would sit up there, take images that he discovered Pluto in. First thing that we found out that it's sort of weird, not quite like any of the other planets that we had known about so far. Here's the inner solar system. This is not to scale, but just, work with us here. That had results here. We're gonna see that in a second. So Pluto is very eccentric. So it doesn't go around in a perfect circle. It gets closer and farther from the sun. It's also tilted like this. So all the other planets lie in a plane, and Pluto is tilted out of the plane. They all rotate, all of these bodies in here basically are rotating up and down. Something weird is going on with Uranus. We're going to talk about that later. Something weird happened to Venus. We'll talk about that later. Pluto's like way off on the side as well. That's a real weirdo. It's got a really, really long orbit. It's really far out there. So this is the end of the Civil War. This is the end of the Civil War over here. This is the guy who founded the observatory that I just showed you. This is the guy who's named the Kuiper Belt. That's the body of icy bodies outside of Neptune's orbit. That's the guy who found Pluto. And when he was just 24, that's him finding Pluto. Pretty cool, right? You're 24 years old, find a planet. And then he lives long enough that it never, I think in his lifetime, is removed as a planet, so he doesn't know. And all of the space races going on, they launch a spacecraft to go look at it, and the thing still has not made one full rotation around the sun. Okay, so you are here, right there. It's still not back to the farthest that it gets away from the sun. Its seasons are weird, and I mean really weird. Okay. Again, its year is 248 years. It gets closer, and it basically it's like a bicycle with wheels. So it's rotating around on its side, and it's rolling like this. So depending on how that axis of rotation, so it's rotating like this. I don't know if you can see that. It's rotating like that, right? So depending on what the orientation of that axis is to the sun, right, you get very different seasons on Pluto. And that's kind of a weird thing, but maybe it's a little hard for us to conceptualize because it's an icy body. Who cares, right? Probably just old and gross and dusty, right? Okay. Pluto is sometimes closer to the sun than Neptune. So that's another weirdo one. So Neptune is, living its best life, the outermost planet, and then Pluto sneaks in front of it, cuts it for a little while, and then heads back out. So Pluto is now back at the farthest out planet. But if you just wait casual 230 years, it'll be the 7th farthest planet. Yeah.
One calculation you said Pluto, it's a so do you know it said it was meter eyes, right?
Right there.
Yeah.
Yeah. So just take this number and we're gonna add 248. Bada bing, bada boom. Yeah, I really wanted to today update this, but I can't see the future. I was gonna go backwards. I was gonna do the beginning of the US, but we'll do that later. Yeah.
So if sometimes Pluto crosses into Neptune, why does that still mean that Neptune's path, orbit, is clear? And sometimes it's
It's very good question. Okay, so this one on the right-hand side, that's Neptune. Okay, this is Neptune from Neptune's perspective. So if the entire solar system rotates with it, it makes these sort of beautiful drawings, which shows, is there any stuff that crosses Neptune's path? And another question you might have is, does Pluto and Neptune ever have the chance of hitting? Right? Which would be a very, standard question if one is at the same distance as the other at some point. But you can see here that this is Neptune, the end, that's Uranus, tracing out a circle. There's Saturn, there's Jupiter, the inner solar system, right? So this is the path of Pluto. You see how it makes these little horseshoes around? So this is a version of clearing out this neighborhood. Not in like the physical space that we think of, but in an orbit-centric space. Because if you're really interested, I can show you another one of these later, where you can see the objects have a very real chance of hitting each other because they live so much in the same region. Right? Great question, though. Okay, anything else about this one? So Pluto not in any danger of being hit by Neptune. And in fact, if it were in chance of being hit by Neptune, it probably would have already been. Right? Yeah.
If the cluster would affect us, or would it just take Pluto years before it affects us?
What do you mean by that?
Oh, I'm visualizing like if Pluto crashes into Neptune or vice versa, like planet like crumbled and splits apart or whatever. I don't know how it works. It's just like, would that affect us down the line?
No, I mean, the nice thing that is about the Earth is that Jupiter actually does a really good job of protecting us. So Jupiter is quite big. And because it's very massive, it's really good at like sweeping stuff up and adding stuff to it. And since we're closer, something's just like haphazardly moving into the inner solar system, much more likely to hit Jupiter than you are to hit us. And in fact, I think I'll find a picture for you of something hitting Jupiter. Yeah.
So if we were like the only planet in the solar system, we'd have a pretty high likelihood of being hit all the time.
Oh yeah. Okay. Yeah. Okay. So some other things about Pluto. Its composition and size doesn't match the pattern that we were seeing. Inner planets are small and rocky. Outer planets, as we're going to see, they're big and gaseous. And then all of a sudden, Pluto's smaller. Right? And so people are like, huh, that's funny. You would think if you're going to make more planets, that you would expect them to have gas. Well, this one does. This one doesn't. So they were like, that's strange. The Hubble Space Telescope is the best optical telescope that money can buy because you just stick it in space. And in space, you don't have an atmosphere, so there's no twinkling effect of any of the stars. So because it's orbiting the Earth, we can take many hours long images just staring at one thing. And that's the best picture we got. Not very good, right? So you take these two images, you're like, huh, I guess it's light in some places and dark in others. Thanks. If you take the Earth's moon and you put it at that same resolution, that's what the Earth's moon looked like. So you can't tell if there's tectonics. You can't see that there's lunar maria, right? There's no mountain ranges possible in an image like this, right? And that was the best map of Pluto until 2015. So it definitely got variational differences, though. It looks weird, right?
Is that due to the camera or?
No. This is like the real, like this is light and this is dark. That's all we know. Light and dark. There's a light up here. That's it. You have it in color. Now we're really getting somewhere. Right? What do you think's on the surface? Any guesses? Clouds? Okay, interesting. Now remember, we're going to talk about size, we're going to think about planetary processes here, right? Do we expect there to be craters on this surface? Yeah, probably, right? Why would there be craters?
So what if you like the surface would be becoming new from a volcano?
Right, yeah, we don't have any reason for there to be volcanism. Tidal heating seems like a no-go, because it's not orbiting a big planet close, right? Deforming the surface. Okay. All right, we'll think about this more. The Kuiper belt is that hypothesized band of small icy objects, probably between 35 times as far from the sun as we are to 100 times as far from the sun. And it's like a belt. Pluto was the first object discovered there. It has this weird orbit. Remember, all the planets are like this, and this guy's like tilted, driving drunk. Okay. So for a long time, Pluto was the only one we knew about. And Pluto was a planet. First object. Okay. And then people started finding more. You see the one with the arrow, right? You see the one without the arrow? Right here. Okay. So there's a planet hunting team. Mike Brown has a book, Why I Killed Pluto and like why I don't regret it or something. And you can read that if you care. It's fine. This work has been led by quite a number of people to find lots and lots of these objects. Okay. Now, again, I'll remind you that they are not emitting their own light. So they're only reflecting light. So what that means is you have a bias. The bias is for things that are big or things that are close or both. Because if you have a mirror and you put it really far away from you, it'll be harder to see it and it's like right up to your eye. Right? Also, you can't change how bright the sun is. So if it's very reflective, you'll see that mirror very easily as opposed to like a very dark rock. Right? Okay. Good question?
Yeah, so how long are these pictures taken apart then, since Pluto takes like forever to orbit last time?
Very good question. Okay, so you have to wait a long fucking time. So these images are taking years.
You know how many years?
I don't remember which ones are which right now, but these would, yeah, this could be like a decade of observation. Yeah, so it's a very, very good question here because some objects in particular, if they're really far away, they're going to be moving really slowly. So even if you're really big, maybe you're not showing up because you're so far away and nothing's moving, right? Or it doesn't look like it. You have to wait like 30, 40, 50 years for it to move enough for someone to notice. Did you have a question? Yeah. Of the original images? Well, he had photographic plates. So if you go to Arizona, you can see the original photographic plates or like replicas of them. But they're not that pretty. You know? The images that we get from New Horizons, I promise, are way worth it. Yeah. Oh no. All right. So at first, finding other objects, yeah, not a big deal, right? You got Pluto. Pluto is named after the dog from Disney Channel, or don't know. What? Which god? God of the underworld, right? Okay. So all of these moons or all of these bodies that I'm about to show you are named after gods, unless they haven't been named yet. Sedna, and I really don't know how to pronounce it, so I'm not going to try. Hora, I think, or something. This is the god of creation from the native people of the LA, like San Gabriel area. So this is a god of creation. This is a god of creation from the Sedna, I believe is of the Inuit people. And so they just started naming, these KBOs after, other traditional gods of creation or destruction, whichever way. You see the one in here?
Up and down.
Right here. Okay, so now the floodgates really open and they start finding tons of these. So here's a bunch more. And the worst news for Pluto is they find a barrel. So this is Eris. And Eris is the god of dysfunction, I believe, or something like that, discord. And dysnomia, the moon of Eris, is the like god of like lawlessness and I don't think it's greed, but it's something like this. It's like not following the rules is dysnomia. So this one here is larger than Pluto. Make is the traditional god of creation of some of the Hawaiian people. Haumea of the Easter Islanders. And we just keep finding more and more. Planet Ceres, by the way, the one that's in our in the asteroid belt, fits in between these two. Orcus. And yeah, these are really good names, right? No. Do you know what this is? Yeah, exactly right. Year discovery, something about the telescope. And I think the number from that year. So I believe this is the name of the telescope and which number from that year. What's that? Well, they all get named, but it has to go through the International Astronomical Union. And so imagine a bunch of scientists having to get together to all vote, yes, we like these names. Yeah.
Different from those, all the ones are rounded out for.
We'll get to that. Yeah. Okay. So now we're really in trouble for Pluto being a planet. Because now it has company. Right? Here's all the orbits. See if you can find your favorite in there. There's Haumea, there's Quaoar, there's Make, there's Orcus and Eris and Pluto. So now the blue is like where all of the planets that you've seen so far lie. And the red is all these other weird ones. So really Pluto is beginning not to look so much like a planet anymore. It looks like the first thing in a different class of objects.
Was there a part or did it like shift over time?
We'll see. Okay, so here's some more of them just for their relative sizes. We found thousands of them. Yeah.
Aries leaving or is it just?
No, it's sort of just not complete there. Sorry. It's just bigger than you think it is.
Okay.
Yeah, it just goes off the screen.
Bye.
Okay. By the way, that's Aries, right? Eris, that's Pluto. So it's bigger, but it spent more time farther away, and we could only see it when it got closer. Right? Okay. Here's Make. Notice that we tend to find the named ones tend to be the ones that we are bigger, found first. And the rest of them are these really wonderful names. Right? Okay. For comparison, there's Ceres. This, of course, is in the asteroid belt. This is the largest thing in the asteroid belt, so there's not like a bunch of these smaller objects in there. And then they also have moons. So we know that, I don't know how to say that still, has Wewa. And so this is the god of creation, and this is the god of the sky. So in the story of the creation for those folks, this was the first one created. First moon, first god, right? So each one of them kind of holds that history too. Pluto has a moon called Charon. If you know the story of Pluto, that makes sense to you. You know what a Hydra is, hopefully. You know what Styx is, the river Styx. Yeah. So they're all just named after these different parts of each of the mythologies associated with the original objects. Okay, how did we figure out there was a moon? In 1978, we saw this weird bulge that came and went. So here on the left-hand side, that's what Pluto looks like. Great resolution, right? And then sometimes it looked like it had like a little bit more light. So this is like this is an image But what they've done here, is they flipped the light and the dark. So you can see, right? That's the light part. And there's all these little flecks of light that are coming out when you take the image. Sometimes you just scatter light taken through the telescope. And sometimes it would look not perfectly circular, but have a little bulge. So this tiny bulge seems to appear, disappear, and appear, and disappear. And from that, they could figure out how fast these two objects were orbiting one another and how big they were. So Pluto and Charon are about that size together. You're going to want to say Charon. That's not right. It's Charon. And you can drive across them. I've driven from here to here in 5 days. So that would probably take me 4. Yeah.
It's actually kind of related, but is that United Kingdom or?
Yeah.
Okay.
Yeah, sorry. This size here to here, is like, 1.5 sizes this way.
Yeah, you think it's small.
Yeah, the UK is real small. Questions about their sizes here? All right, let's relax. So we have Pluto and Charon. Another thing I want you to notice, they're small, right? They're small relative to the moon, which is the line here in green. But also, they're relatively big relative to each other. I want you to think for a moment how big the moon is compared to us, right? The Earth, when you look at the map of the Earth, US, we like to think of ourselves as the greatest country, blah, 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 biggest part of the Earth. That's not true, not even close. And the moon, of course, is a small fraction, right, of that entire body. Whereas Charon here is pretty big in comparison to Pluto, ostensibly the thing that it's orbiting, right? Okay. All right, let's keep our brains awake. We're going to think a little bit about numbers. I know this hurts, but it's okay. We can use Charon to weigh Pluto and figure out what its density is. You don't want to know the math on that, I promise you, but I promise we can do it. And we found out that Pluto has a density of about 2 grams per cubic centimeter. Now, water is 1 gram per cubic centimeter. Ice is like 0.98. Rock is between 2 and 3.5. And metals are like 5 to 9, depending on which one you're thinking. Okay. So we already can start thinking about what is Pluto made of. Raise your hand for rock. Raise your hand for metals. Raise your hand for water. Raise your hand for a mixture of rock and water. Okay, all right. That's where we want to be thinking. With a very simple number, we shouldn't overthink this one, right? I'm not telling you exactly what's going on here. In the back of our head, we should be thinking, okay, it can't be pure metal. For example, the Earth is something like 3.5. And Mercury is very similar, something like 3.5. So this is probably more icy than the Earth or the Moon or Mercury, right? For comparison, Jupiter is like 1. Jupiter would float in a pool. Okay, Saturn would float in a pool. I mean, it'd be a big pool for, never mind. All right, let's go. Another thing about them is that they face, just like, for example, our moon shows the same face to us. They show the same face to each other. So if you and your cousin, the ones in blue here, you're looking at each other. One of you standing on Pluto, the other standing on Charon. You can just like keep talking the whole time. Never have to put the phone down because you rotated out of view. Okay. Whereas if you're on the far side, you won't ever be able to communicate with your cousin. So for example, when the astronauts went behind the moon, they could no longer call home. You know why? There's a rock in the way. Radio waves do not go through rock. Okay. they do bounce off the top of the atmosphere so that you can make a phone call anywhere. Or where that doesn't work, we have satellites. But there's no way to talk around a planet. So if you're on the far side here, unless you have a bunch of stations that bring your communication over to blue, you'll never get to talk to red. That's the hypothesis. But basically, these two sides, the red side and the red side, never see each other. And the two blue sides always see each other. Is that fair? This is called, well, you don't memorize it. But they show the same face. Okay. This is what it looks like from the late 1980s. They are rotating on their side like this. So Karen is going around Pluto. All right. And it's even more complicated than that, because even though Charon goes around Pluto, Pluto goes around Charon. So Pluto is making these little wobbles, and Charon's making these big wobbles. So when you're looking at it from above, they do this together. Right? Does that make sense? Oh, it didn't make sense, so it's fine. Okay, so this one goes around the center of mass. When it's over here, this one's way over there, right? Okay. And in 1988, we could watch a star go behind the planet, and we can see there's an atmosphere. So this would be just the same as me putting my hand in front of all of your faces and recording when I saw and didn't see you, right? My hand doesn't have an atmosphere, it doesn't. As soon as it goes across, you can't see it. But just like we have lunar eclipses that bend light because of our atmosphere and make the moon look red, right? The light that's bent. If there is a flat wall here in the light, that means there's no atmosphere. If it's curved at all, that means there's an atmosphere. The light is bending. Okay? And that's what we saw. So with the Pluto and star, you have the total light up here, and then there's a bend, and then there's just Pluto, and then the star reappears from the other side. And from that shape, you can tell basically that there is an atmosphere. Very weird if you think too long. This thing is small. This thing is cold. And it has an atmosphere. Okay. This is the system, essentially. This is what we think. We think that even though there's just a little bit of sunlight, it's enough to warm up the ices and make this atmosphere. But then probably we think in 2006, that all this is just going to escape like a comet. There's no reason for it to hang around. It's going to be boring, right? And it's all going to be blown away. So we sent a spacecraft to go look at it. Okay. This is where we put the radioactive generators. And this is how we communicate home. The other side of that dish. That's us. Okay. We designed it in 2003. People are alive then. All right, I'm gonna skip through all these phases then. Built, designed in Colorado, amongst other places. It was designed fully in 2005. They spin it real fast to make sure that it can stand being in space. If you ever think you're having a really bad day, just remember there was one time, this is called the spin test. And you keep it in place by putting giant rods, essentially. Okay. And someone needed them for another test. So they pulled them out, walked over to this other test, ran it, and then forgot to put them back. And this, not for this spacecraft, but for another spacecraft, they turned that spin test on. It immediately fell over and $1 billion spacecraft was ruined. So your day is not as bad as that person's day was, right? For work. For work. Oh, I'm sure he got fired. Okay, so this is how we sense the spacecraft, or these are the instruments that we sent to Pluto. This one takes high resolution black and white images. That's called LORI. This one was designed by students to test the dust environment from the University of Colorado. It's gonna do a really weird thing when we watch this video of the close encounter. So it's going to try and thread the needle. It's gonna pass behind Pluto's shadow, and then ideally behind Charon's shadow. Okay, it's gonna fly in between the two of them, right? Gonna fly in between the two orbits and try and get behind both of them. Okay. The whole thing happens within 2 hours. So it launches in 2006, takes 9 years to get there, and all the data has to be taken in less than 2 hours. And then it'll spend 2 years sending that data back. So it's going to store it on its onboard computers and then very slowly send it back to us. Just before it got there, just weeks before it got there, we found 2 more moons. So they wanted to look to make sure that the place that they were going to fly didn't have stuff in the way, right? Good thing they did. And they found Kerberos and Styx, which were interior moons. So there's a bunch of moons going around Pluto. There's the location that New Horizons is going to go. Can I show you guys the video, or do you want me to turn the lights off? And okay. All right. That's the relative sizes. The whole system is moving at 3,300 miles an hour at this time. And I'm going to go ahead and just skip to the video, and then we'll come back to this and we'll talk about the science afterwards. Okay. What do we expect to see? Not a lot, right? So it's small. So we expect no tectonics. We don't expect volcanism, right? Lots of impact craters, right? Okay. Atmosphere somehow, but we don't really understand why. All right. If this doesn't play, I'm really going to be upset. Okay. These are real images. Every single one is a real image. So that's passing behind first Pluto. And then that was Charon on the right. And we took images of both. We're going to watch it multiple times here. As you look very closely, let me know if you see, I guess that's pretty too fast. Remember in those original images, some of it was dark and some of it was light? It's dark and light. Okay. We're going to jump more into the planetary geology when we start on Thursday. But if you haven't given me your check-in, please do so here. If you didn't notice, there's a homework posted. I apologize. It was there. I just didn't publish it. So if you want to complain to me, that's perfectly okay. Hi.